Hello everyone. In today's lesson, we're going to be looking at limits of functions at infinity. So first of all, let's look at our limits at infinity. So we have the notation, we take the limit of some x as it goes to infinity on the function f of x equals L. This means that our function f of x will go to L as x approaches infinity. So our line y equals L is the horizontal asymptote if our limit of f of x equals L, or if our limit as x approaches negative infinity equals L. So that is to say, our limit as x approaches infinity, f of x, is equal to L, or our limit as x approaches negative infinity equals to L. And these are our limits at infinity. Now I want to note here that infinity is not a real number. So even though we write that limit of as x approaches infinity, f of x equals L, the function is divergent if the limit is either plus or minus infinity. So if you get the limit is equal to plus or minus infinity, it's actually divergent. And since infinity is not a real number, not all of the normal operations that we do hold. So for example, we might have infinity plus infinity equals infinity. So I just add some infinitely large number to some other infinitely large number, I'll still have infinity. If we did infinity times infinity, same idea. If I have some infinitely large number and I multiply it by some infinitely large number, I still end up with infinity. But if I have infinity minus infinity, well, what does this even mean? So in this case, this would be undefined. And similarly, if I have infinity divided by infinity, this would also be undefined, because what does it mean to take some infinitely large number and subtract off some other infinitely large number, or take some infinitely large number and divide by some infinitely large number? So as an example, looking at this graph, what would be our asymptotes based on this graph? Well, as x goes to infinity, which means that we're going to the right here, you'll notice that it looks like this line is approaching positive 3, but never actually touching it. So this would be the asymptote, or the limit, as x approaches infinity. As x approaches negative infinity, that is going on our graph to the left, it looks like this line is approaching negative 2, but never actually touching it. So this means that our limit as x approaches infinity on our function f of x is equal to positive 3, and the limit as x approaches infinity, negative infinity, on our function f of x will be equal to negative 2. So this means that we have y equals negative 2 and y equals 3. These are the two asymptotes that this function is approaching as the limit approaches infinity or negative infinity. In this example, we want to find the limit as x approaches negative infinity on the function 1 over x. And we want to try to figure out what this is equal to. And we also want to see what is the limit as x approaches infinity on our function 1 over x. So if we were to look at the behavior of this function, what happens as we go with larger and larger and larger numbers to the right? So as our x increases, we'll start with the going to infinity. Well, if I plug in 1, I'm going to get 1 over 1, which is 1. If I plug in 2, I'm going to get 1 over 2, which is 1/2, 1/3, 1/4, 1/5. So what's happening is as I go to the right, I'm getting closer and closer and closer to 0. So I'm just going to kind of draw it like this for now. Now what happens with this positive x approaches infinity, but as I get closer to 0, right? Because I know that I cannot plug 0 into this because I would end up with 1 over 0. So if I plugged in 0.5, I would get 1 over 0.5, which is equal to 2. If I plugged in 3, I would get, if I plugged in 0.3, I would get 1 over 0.3, which is going to be 3.3, something like that. So what's happening is as this value gets closer and closer to 0, the entire thing is getting bigger, meaning that it's going to be approaching infinity as it approaches 0. Similarly, if I'm looking at x that go to the negative infinity direction, if I plug in larger and larger x values that are negative, so -1, -2, -3, so on and so forth, it's going to get smaller and smaller and smaller, and it's going to approach 0. If I get closer to 0, so as I approach 0 from the left, what's going to happen is this is going to get smaller and smaller and smaller down towards negative infinity. So this would be a graph of what this function looks like, meaning that if I look at what happens as x goes to negative infinity, it's approaching 0. So this is going to be equal to 0. And if I look at what's happening as x approaches positive infinity, this is also going to be 0. So in this case, the limit as x approaches infinity is equal to 0. The limit as x approaches negative infinity is also equal to 0. So now that we have an intuitive idea of what it means to take a limit as x approaches infinity or negative infinity, let's look at what we would do if, we're using a couple examples, if we had functions that weren't so easy to visualize and we wanted to solve it analytically. So we're going to start with, in this case, the limit as t approaches infinity, 8t divided by 1 plus 4t squared. So in this case, I don't know what this function looks like on a graph off the top of my head. Now, I could put it into a computer or calculator and probably look at it, but sometimes you're not going to know what the behavior is off to infinity by just looking at a graph in a local frame. So you might have to zoom out, zoom out, zoom out. It's easier just to say, okay, well, let's just solve for what this is equal to as I approach infinity. And usually the first trick we do is we plug in infinity and see what happens. So in this case, if I were to plug in infinity, anywhere there's t, I would get 8 times infinity, which is equal to infinity, over 1 plus 4 times infinity squared. So infinity squared is infinity, 4 times infinity is infinity, 1 plus infinity is still infinity. I end up with infinity over infinity. So as we talked about, this is undefined. So that really didn't tell us anything. So now what we're going to do is we're going to try out some of our tricks. So our first trick we talked about was dividing the entire thing by the highest power of whatever parameter we're looking at, in this case t, divide everything by that t squared. So this would be the limit as t approaches infinity, 8t over t squared, divided by 1 over t squared, plus 4t squared over t squared. Now, of course, I'm going to do some cancellation. This t will cancel with one of these t's. This will be 1 over t squared, and the t squares will cancel here. So now what we're left with is the limit as t approaches infinity, 8 over t divided by 1 over t squared plus 4. Now, at this point, most people would just solve it by, again, going back to plugging in t to see what the behavior is. But just to be more explicit, what I'm going to do now is I'm going to use our limit rules to actually show how we're actually solving this. So first things first, I have limit of something in the numerator over something in the denominator. So this is actually equivalent to saying that I want the limit as t approaches infinity, 8 over t, divided by, now I have the limit as t approaches infinity, 1 over t squared plus 4. Which can then be split into the limit of the first thing plus the limit of the second thing. So this is then going to be the limit as t approaches infinity, 1 over t squared, plus the limit as t approaches infinity, 4. And now that we have it in this form, we can actually solve for it, because we have this 8, which is constant, so I could pull this out. And this is going to be the same thing as actually taking 8 times the limit of 1 over t as t approaches infinity. This one, we don't have to actually make any change, so I'm going to leave this one, limit as t approaches infinity, 1 over t. And then this one also doesn't need to be changed. So plus limit as t approaches infinity, 4. Now we can actually look at all of our individual limits. What is the limit 1 over t? And we covered this previously, is what's going to happen is as this t gets bigger and bigger and bigger, it's going to be 1 over 1, 1 over 2, 1 over 3, is that this entire fraction is getting smaller and smaller and smaller until it goes to 0. This bottom term, same idea. We have 1 over t squared which is going to also go down to 0. And then limit of a constant is just going to be that constant. So this is going to be 4. So we're left with 0 over 0 plus 4, which is 0 over 4, which is equal to 0. Next, we're going to look at the limit as x approaches infinity. And this is going to be on the square root of x squared plus 1 minus x. Now, in some cases, you're not going to be able to use the trick we talked about where you just divide by the largest power in the denominator, because in this case, we don't really have a denominator to a fraction. So we're going to need to use a different trick to be able to solve this, because if we were to plug in infinity, infinity squared is infinity, infinity plus 1, still infinity, the square root of infinity, still infinity, because that would just be infinity to the 1/2 power. So we'd have infinity minus infinity, which again we said was undefined. So what we're going to do in this case, if you ever see a term kind of like this, is we're going to do what's called multiplying by the conjugate. So the conjugate of this term is the same terms, square root of x squared plus 1 and x, except for now we're going to switch the operation from subtraction to addition. So this is going to be the limit as x approaches infinity, the square root of x squared plus 1 minus x, and then we're going to multiply this. So we're going to think of this as a fraction over 1, and we're going to multiply this by square root of x squared plus 1 plus x divided by square root of x squared plus 1 plus x. Now, the reason I can do this is because any term over itself, square root of x squared plus 1 plus x over the same thing is the same thing as just multiplying this entire function by 1. So I haven't changed anything. So now what we need to do is we need to multiply this out. So for the bottom, we're just going to multiply 1 times this. It's going to stay the same. So this is going to be the limit as x approaches infinity. And this is going to be the square root of x squared plus 1 plus x. And in the numerator, we're going to have to FOIL this out. So we're going to do first term. So the square root of x squared plus 1 times the square root of x squared plus 1 is the same thing as saying the square root of x squared plus 1 squared. So the square and the square root will cancel. We'll just be left with x squared plus 1. Then we're going to do our outer terms. So we're going to have the square root of x squared plus 1 times x and then we're going to do our inner terms, minus square root of x squared plus 1 times x. And this is actually why this trick works out so well. And then we'll do our last terms. Minus x times positive x is going to be minus x squared. So now looking at this, what do we have? Well, we have x times square root of x squared plus 1 minus x times square root of x squared plus 1. These are the same terms. We have a positive and negative. These two will cancel with each other. And if you remember, here we had x squared plus 1 minus x squared. So this x squared is going to cancel with this minus x squared. So this is going to leave us with the limit as x approaches infinity, 1 divided by the square root of x squared plus 1 plus x. And then, of course, using our rules of limits, I could change this to the limit as x approaches infinity of 1 over the limit as x approaches infinity, square root of x squared plus 1 plus the limit as x approaches infinity, x. So the limit as x approaches infinity on a constant 1 is just constant 1. The limit on x squared plus 1, you take the square root of the whole thing. We talked about this already. Infinity squared is infinity. Infinity plus 1 is infinity. Square root of infinity, still infinity. Plus, the limit as x approaches infinity on x is just going to be infinity. So we have 1 divided by infinity plus infinity, which is the same thing as saying 1 over infinity, which means that this goes to 0. Now, sometimes when you're dealing with certain functions, for example, trig functions, you might actually not be able to just take the limit, but you'll have to kind of look at the behavior of the function as it approaches infinity or negative infinity. So let's say, for example, that we were evaluating the limit as x approaches infinity, sine of x. So in this case, if you plug in a value, you're going to be getting values back based on your trig functions. But what happens with the actual behavior of our sine function? Well, sine function, starting at 0, will start at 0 in your, so when x is 0, y is 0, and then it's going to go up to 1, and then it's going to go down to -1, and then it is going to have this cycle, right? And of course, we have that this is going to be pi over 2, pi, 3 pi over 2, and 2 pi. Right? So this is when x is equal to pi over 2. This is when x is equal to pi. This is when x is equal to 3 pi over 2. And this is when x is equal to 2 pi. And then what's going to happen is it's going to repeat this. And it's going to repeat it. And it's going to repeat it over and over and over again, and in both directions. So it's going to be going from -1 to +1, repeating. Meaning that as I go to the right towards infinity, I'm just going to keep cycling between +1, -1, +1, -1. So in this case, when we have this limit as x approaches infinity, sine x, we have does not exist as our answer, because there is no limit that exists, right? It's divergent in the sense that it does not converge on any specific value. It doesn't converge to 0. It doesn't converge to some L. It just will cycle back and forth between negative infinity and positive infinity. For our next example, we're going to be looking at the function x cubed. And we want to know what's happening as you take the limit as x approaches infinity and negative infinity. So we'll start with the limit as x approaches infinity, and we'll also look at the limit as x approaches negative infinity on x cubed. So what's happening as I take my x and it gets larger and larger? Well, first of all, let's see what happens when we have x equals 0. So if I plug in x equals 0 here, 0 cubed is just going to be 0. So I'm going to start right here. If I plug in 1, I'm going to get 1 cubed, which is going to be equal to 1. If I plug in 2, I'm going to get 2 cubed, which is going to be 2, 4, 8. So it's going to be something over here. If I plug in 3 cubed, it's going to be 27, and it's going to grow very quickly. So on the right side, we know that this is kind of what the behavior looks like. It's going to grow very rapidly on the right side. Now, what about if I starting at 0, I start plugging in negative values? Well, I have -1. -1 cubed is going to be -1. -2 cubed is going to be -2 times -2 is +4. +4 times -2 makes it -8. And then we're going to get -27, and it's going to look something like this. So based on this, what's happening as to x cubed as we go to the right as x approaches infinity? It's going to go to infinity. And what's happening to the left as x approaches negative infinity? It's also going to go to, in this case, negative infinity. So what's happening in this case, because this is an odd function, when I have positive values, I'm going to the right, I'm growing faster and faster and faster upward towards infinity. When I go to the left, my negative values will get smaller and will shrink smaller and smaller and smaller towards negative infinity. The next thing I want to talk to you about, though, is that not all infinities are equal, right? Because sometimes, because we're looking as x approaches infinity, or whatever variable we're looking at the rate that it grows or decays. Well, what if you have multiple things that go to infinity, but they grow at different rates? Well, then sometimes this will mean that one will grow faster than another, which actually can lead to the entire function converging to usually 0 or something like that. Or infinity. So let's look at what's happening with these. Let's say that, for example, we had the limit as x approaches infinity on e to the x. We have the limit as x approaches infinity, x squared. We have the limit as x approaches infinity, square root of x. And we have the limit as x approaches infinity, natural log of x. So what we're going to do is we're going to graph this out. So all of these, we're just going to look at what happens as x goes to infinity. So we're only going to be looking in quadrant 1 of our graph, of our Cartesian graph. So if we were to graph e to the x, it's going to look something like this. and this is our e to the x. If we were to graph x squared, it'll look something like this. If we were to graph our function square root of x, it'll look something like this. And if we were to graph our natural log of x, it would look something like this. So all of these do actually go to infinity, right? Because if I plug in e to the x, as my x gets bigger, my exponential causes it to grow very rapidly. Same thing with x squared. If I plug in 1 squared, it's 1, 2 squared is 4, 3 squared is 9, 16, 25, so on and so forth. It's getting larger and larger towards infinity. We already looked at square root of x before in our prior section, where again, if I plug in numbers, square root of 1 is 1, square root of 4 is 2, square root of 9 is 3, square root of 16 is 4. So what's happening is while it's growing very slowly compared to the others, it is growing up until infinity, right? If I plug in square root of infinity, I get infinity. And last, I have my natural log, which also grows very slowly, but it does continue to grow on to infinity. So now you can kind of see how these grow at different rates. So for example, if I were to take something like the limit as x approaches infinity, e to the x over the natural log of x, these are both going to infinity. So you might think just by plugging infinity that this is going to be infinity over infinity, which is undefined. But you can also use the relationship that while they are both going to infinity, this term is growing so much faster than this term. Or what if I had it the other way? What if I had the limit as x approaches infinity, the natural log of x over e to the x? Well, in this case, the denominator is growing significantly faster, meaning that while they're both going towards infinity, the bottom term is getting bigger faster, meaning that the total fraction is getting smaller, meaning that this one is going to converge to 0 in this case. So let's look at an example of this. Let's say that we have the limit as x approaches infinity, x squared minus x. So in this case, we were to just plug in our infinity, we would get that this is limit as x squared would be infinity, minus limit of x would be infinity. So infinity minus infinity, of course, is undefined. So now what I'm going to do is I'm actually going to look to see, is the behavior different if I were to pull this x out? Because I have x squared minus x. Both terms have x. So I could rewrite this as the limit as x approaches infinity. I pull an x out, and x squared, pull an x out, I'm left with x, minus x, pull the x out, I'm left with 1. Now if I were to take this limit, which again I still can by my rules of limits, right? I could take the limit of x squared minus the limit of x, or I could take the limit of x times the limit of x minus 1. So I'm going to get the limit as x approaches infinity, x times the limit as x approaches infinity, x minus 1. So this will be equal to infinity times infinity minus 1, which if we consider what's happening here is that this infinity squared is growing faster than this minus infinity, which we could kind of figure out intuitively here. X squared is growing faster than the x that is being subtracted from it. So in this case, our limit would be, in fact, infinity. So let's do one more example here where we have limit as x approaches infinity, x squared plus x divided by 3 minus x. So first thing I'm going to do is I'm going to use our trick where I'm going to divide everything by the power of whatever the largest power is in the denominator. Because if I were to plug in infinity right now, I'd get infinity plus infinity, which is infinity, divided by 3 minus infinity, which is negative infinity. So I'd get infinity over negative infinity would equal undefined. So in this case, what I'm going to do is I'm going to divide everything by x. So this is going to be the limit as x approaches infinity, x squared over x plus x over x divided by 3 over x minus x over x. Now, doing some cancellation, this x cancels with this x squared. This x cancels out with this x, leaving me just 1. This 3 over x is fine, and then x over x gives me 1. Now, this leaves me with the limit as x approaches infinity, x plus 1 divided by 3 over x minus 1. And now with this, I actually could probably try plugging in infinity again and see what happens. So if I were to do this limit, really what's happening is it's the limit of the top over the limit of the bottom, which then this top becomes limit of x plus the limit of 1 over the limit of 3 over x minus the limit of 1. So what's going to happen is these constants will stay constant. This is going to go to infinity, and this is going to go to 3 over infinity. So this is going to be infinity plus 1 divided by 0 minus 1. Now, infinity plus 1 is just equal to infinity. 0 minus 1 is going to be minus 1, which means that I have infinity over negative 1, which is the same thing as saying that this goes to negative infinity. For my next example, we have the limit as t approaches infinity, square root of t plus t squared divided by 2t minus t squared. So I'm going to use the same trick. I'm going to divide everything by the largest power denominator. In this case, it's going to be t squared. So this is going to be the limit as t approaches infinity, square root of t over t squared plus t squared over t squared divided by 2t over t squared minus t squared over t squared. So the t squares cancel. This leaves me 1. This one just leaves me 1. This t cancels with one of the t's here. Now this one, this is where you need to think about your powers, because the square root is the same thing as saying t to the 1/2. So what I can do is I can actually take this square root of t over t squared, and I can rewrite this as 1 over t to the 1/2, right? Sorry, negative. Because what I'm saying is by the t to the 1/2 is saying take the square root. The negative power is putting it into the denominator. So now I have 1 over t to the negative 1/2 times 1 over t squared. And of course, whenever we multiply t to a power times t to a power, you add the powers. Or in this case, because it's negative, we're going to subtract it. So it's going to be 2 minus 1/2, which is going to give me 1 over t to the 3/2. So this leaves us with the limit as t approaches infinity, 1 over t to the 3/2 plus 1 divided by 2 over t minus 1. So now that we're at this form, we should be able to plug in our infinity to see what's going to happen, right? Because again, laws of limits, if you do the limit of the top over the limit of the bottom, limit of the top becomes limit of the first term plus limit of the second term, limit of the bottom becomes limit of the first term, in this case minus limit of the second term. So 1 over t to the 3/2. What's happening with this in the denominator? Square root of t cubed. Well, what's happening is that this t cubed is growing faster than the square root is slowing it down, meaning that it's going to approach infinity. So we have 1 over infinity, which means this is equal to 0, plus 1, divided by, as I plug infinity into 2 over t, this is going to be 2 over infinity, which is equal to 0, minus 1. So I'm left with 1 over minus 1, which is equal to negative 1. For our last example, we're going to look at the limit as x approaches infinity, square root of 9x squared plus x minus 3x. So just like we looked at before, this case, if we plugged in infinity, we're going to get 9 infinity squared. So infinity squared is infinity. 9 times infinity is infinity. Infinity plus infinity is still infinity. Square root of infinity, still infinity. We're going to get infinity minus 3 times infinity, which is infinity. So infinity minus infinity, which is undefined. So we can't just plug in and see what it converges to. So the next thing we're going to do is we're going to say, can we divide by some power denominator? Well, in this case, there's no denominator because it's not a fraction. So we're going to then use our next trick, which was to multiply by the conjugate. So in this case, this would be equal to the limit as x approaches infinity. So we'll just write this again. This will be the square root of 9x squared plus x minus 3x. And then this is going to be times. Now, if you remember, the conjugate is going to be the same two terms, but we're going to change this operation. So it'll be square root of 9x squared plus x plus 3x. So this will be square root of 9x squared plus x plus 3x divided by the square root of 9x squared plus x plus 3x. And of course, this is the same thing as saying this is over 1, because any value that you have, you can always think of it as a fraction over 1. So we're going to multiply these out. So for the denominator, this is just going to be the square root of 9x squared plus x plus 3x. For the numerator, what we're going to do is we're going to multiply. Square root of 9x squared plus x times square root of 9x squared plus x. It's going to give me square root of 9x squared plus x squared. So the square root and the square are going to cancel, which is going to leave me with 9x squared plus x. Then I'm going to do my outer term. So that's going to be 3x times the square root of 9x squared plus x. So this is going to be 3x times the square root of 9x squared plus x. Next thing I'm doing my inner terms, minus 3x times the square root of 9x squared plus x. So this is going to be minus 3x square root of 9x squared plus x. And then I'll do my last terms. Minus 3x plus times 3x is going to be, so negative 3 times 3 is going to be 9x squared. So there's going to be minus 9x squared. So now let's look and see if we can do some cancellation. Well, first things first, 9x squared and minus 9x squared. So the negative and the positive cancel with each other. 3x times the square root of 9x squared plus x minus 3x times the square root of 9x squared plus x. These are going to cancel with each other. So we're just going to be left with x in the top. So this is going to be x divided by the square root of 9x squared plus x plus 3x. So now let's see if we can plug, sorry, I forgot my limit. So now what we're going to do is we're going to see, can I plug in, by the way, you always need to leave your limit in the formulation of what you're doing until you've actually solved and plugged in that limit. So sometimes you might see, like, for example, here, I forgot my limit. This is incorrect because it is still the limit as x approaches infinity. The limit does not go away until you actually evaluate the limit at whatever x is approaching, or t, or whatever we're using. So in this case, you do need to keep your limits until you actually plug it in. So if we were to plug in our limit, infinity divided by, well, we talked about the square root of 9x squared plus x. If you plug in infinity, it's going to be infinity plus infinity. So infinity over infinity, still undefined. So now what we're going to do is we're going to do our other trick, and we're going to divide by the largest power in our denominator. So in this case, it's going to be x. Now, you might see, okay, well, I have an x squared here, but if you look at it, it's actually the square root of an x squared, so it's still going to be x. So I'm going to divide everything, so I have my limit, didn't forget it this time, as x approaches infinity, x over x divided by the square root of 9x squared plus x divided by x plus 3x divided by x. Now, this x over x is going to cancel, leaving me with 1. This x over x is going to cancel, leaving me with 3. So now I have the limit as x approaches infinity, 1 over the square. What I'm going to do is I'm actually going to pull this x inside. So I can think of this x as the square root of x squared. So by doing that, this term here is going to become 9x squared plus x over x squared under the square root, which then is the same thing as dividing this by x squared, dividing this by x squared. So this is going to be 9x squared over x squared plus x over x squared, all into the square root. and this x squared is going to cancel with this x squared. This x squared is going to cancel, sorry, this x, one of the powers of x here is going to cancel with this x. This is going to leave me with the square root of 9 minus 1 over x. So using that, we have the square root of 9 minus 1 over x plus 3. And then I'm going to plug my x in at infinity. So this is going to become 1 divided by, so the square root of 9 minus 1 over x. Plug in infinity into that x, we get 9 minus 1 over infinity. 1 over infinity is going to, as the denominator gets bigger and bigger, the entire fraction gets smaller and smaller. Same thing as saying 9 minus 0. So this is going to be the square root of 9 and then plus 3. Well, the square root of 9 is going to be, by the way, the limit is gone here because now I've evaluated it. So this is going to be 1 over, so the square root of 9 is 3, so 3 plus 3 is going to be 1/6. And that's all you need to do in order to evaluate a lot of these limits as x approaches infinity or negative infinity. Now, you'll notice in this section I've been using a lot of tricks. And the thing is, sometimes you are not going to be able to evaluate a function based on just being able to plug in the value, or there might not be some trick that we can use. And later on, we will talk more about this. Numerical methods, or another method we'll talk about later is L'Hopital's rule, which will allow us to evaluate, in this case, indeterminate functions based on trying to solve what this is equal to, right? So right now, when I'm doing a lot of these examples using analytic approaches, these are examples where we know that it's going to give us an answer that we can find analytically.
Thank you for watching. To continue learning, click the linked video here for the next lesson. If there's a topic you'd like me to cover, let me know in the comments. Don't forget to subscribe, and I'll see you in the next video.